manifold. And then convention. You all were in the fall, right? Here, so you're familiar with this. Just say yes. You've seen that? No. Okay, just don't be afraid. So this just means that whenever you see, well, let's say you have AI here, when you write something like this, there is an index that is repeated. It's the same index. Then what it actually means is the sum I from 1 to n AI. So these sums appear everywhere, and there are so many of them that they would really complicate the notation. That's why we just don't try that. We write this, but this means that. So whenever you see an index that is repeated, then it means that there is a summation goal. This is called Einstein's summation convention. Well, of course, you could have more than one pair of repeated indices, then there are more sums. Okay? So that's one thing, and then another like vector fields. Well, let's say vector field X. So vector fields are identified with differential operators. So vector field is, by definition, something like this. Well, this little x, these are the coordinates, and this capital X is the vector field, and then there is dI, and of course this means that there is this sum. I just don't write this. So that's a first order partial differential operator with variable coefficients. Well, usually we would call this a vector field. Well, that's a vector. I goes from 1 to n, that's a vector, right? But this is not an invariant notion, because when we change the coordinates, this will change. And so if you define this differential operator, this is invariant, because that's the same in all coordinate systems. If you change the coordinates, then the partial derivatives change according to the chain rule, and this chain according to the chain rule, and so that the whole thing is invariant. We talked about this in the fall, right? So that's why I just want to remind you this. So the first one is the divergence of a vector field. So how is it defined? Well, to do it, I need to remind you what is a Lie derivative. Well, let me just write this first and then explain what it means. Divergence of a vector field. So you need a vector field. Now let X be something like this. Well, in specific coordinate system, it has this form. I mean, if you, this capital A is always a different thing than the little a, which is the X, which is the coordinate. So that's a vector field. Then let omega be volume form. What is a volume form? Well, if you remember what are differential forms in general, the differential forms are things like this: dx1 dxn. Well, that is an n form. If you don't remember this, I'm not going to talk about this, because that would take too much to explain. So the volume form is an expression like this, where here is some function, and so if you have a metric, let me just write this. That's a canonical form if Gij is the Riemannian metric. So what is this metric? Well, this metric allows you to define an inner product of vectors. So if we have one and then we have another, then that will be gij xi yj. And of course there is sum over I and sum over j. So an inner product requires metric. So once you have a metric, you can do this. What is that G? Well, that G is the determinant of that, of this matrix. Okay, and then you take square root of it, and that defines your so-called Riemannian volume element. Well, if in general this omega could be arbitrary, say positive function, but if you have a metric, then this choice makes a lot of sense, and that's kind of called Riemannian volume. So once you have this, then, well, if you have a vector field, you could define the Lie derivative along that vector field. So the Lie derivative let me just write it in index notation component. So the Lie derivative of a function is just equal to vector field applied to that function. Vector field, remember that it's a differential operator like this. So it's the first order operator applied to the function. So in other words, it is xi dif. So the Lie derivative along x of another vector field, so y is a vector field, is a new vector field such that its components are equal to xi d I, well, let me call it j minus yi di xj, which is nothing but the so-called commutator. This is the commutator of this differential operator. Well, if you write it without index, it's just that. So that's the Lie derivative of a vector field. Well, in components, it's just this. You take these functions, you differentiate. This is basically a directional derivative along f. This one is directional derivative of a scalar function. This is directional derivative of component minus directional derivative along y of the component x. So, and you could also define the Lie derivative of all tensors in particular forms. So, for example, if you take one form, what is it? Well, a covector, which is the same as one form, is something like this: alpha I, which depends on x, dxi. Of course, there is sum here over I. So basically, it is this quantity that gives you, that defines the components of that. So if you know the components, you will know the covector of one form, in particular coordinate system. So the Lie derivative of such a covector is equal to that. Again, you take the directional derivative of the component. This first term is always the same. It's like the scalar function. And then there are other terms. Like here there is this term, and here there will be a term like this. So let me put I here. Well, you say, where does it come from? Well, we could go, I mean, you are in the geometry class, you'll study this and you'll derive all that. But there is a way to write it for any form. So for, say, for 2 forms, 3 forms, and so on, there is a similar formula. And then the Lie derivative along x of the volume form is, well, because this is an n form, the Lie derivative is also an n form. An n form is an antisymmetric n tensor, and therefore there is only one up to the constant. So it will be proportional to the omega. And here the coefficient of proportionality is called the divergence of a vector field. So that formula can be taken as a definition of the divergence. Basically, what does it say? It says, well, you have that vector field. Every vector field defines a flow. Remember that flow kind of, well, let me remind you what the flow is. So if you have xi, the vector field, then, well, it defines a flow is kind of a map like this, so that, well, let me call it F. So in other words, these are the curves. It's a family of curves such that at every point, the tangent vector, this is the tangent vector, is exactly equal to that vector field. So given the vector field, basically the flow of the family of integral curves of that flow, of that vector field. Okay, so for any vector field, there is a corresponding flow. All we need is just to integrate these equations, the system of n differential equations. Well, and then what the Lie derivative basically measures how an object, a geometric object, changes along the flow generated by this. So, for example, if you take here a little volume and you go with the flow, then it will kind of spread, or it will change in a certain way. So that formula measures how the volume, the rate of change of the volume along the flow generated by the vector field x. So if the divergence is 0, then this means that this is 0, which means that it doesn't change at all. And that means that the volume is invariant. And that justifies the notion of the divergence. So in other words, it diverges, but if the divergence is 0, then it means that the volume is kind of invariant. So that's the definition. And of course, there is a formula for that. The divergence of a vector field is, well, it's a scalar function. So this is an n form, this is an n form. This is just a scalar function. And there is a formula for it. Well, let me say, well, in local coordinates, and this looks like has the following form. It is that. Of course, again, there is a sum because there is a repeated index I. So, for example, if Gij is delta ij, so you have Euclidean metric, then G is equal to 1, the determinant of the unit matrix is 1. Then, of course, the divergence will be just equal to Gi xi, which is the one that you've seen in calculus, right? So, of course, there is some I from 1 to n. So this is the divergence. But in curved manifolds, in any manifold, this is a little more general formula when you have this. It comes from, exactly from this place. And that comes so that when you integrate it, it becomes invariant. If you make a change of coordinates here, well, I can prove that this is invariant. It's kind of straightforward. So if you say, if you do change of coordinates, I just call it diffeomorphism. Let me call it x prime I, so this is x prime I of x. So these are new coordinates. So if you do that, then you know that dx prime I is equal to dx prime I by dxj dxj. And of course, there is sum again over j. Right? It's just a chain rule. And then, well, if you do dx prime 1, dx prime n, that's equal to dx1, dxn, and here you'll have exactly the determinant of that matrix. And that is called the Jacobian. Right? So, this one, I mean, you could say, why can't we use this polynomial? Well, because it's not invariant. It requires this Jacobian every time you change coordinates. But at the same time, the metric also changes